Welcome to our journey into the fascinating world of conic sections. Imagine slicing through a towering three-dimensional double cone, a cone with two identical parts extending infinitely in opposite directions with a two-dimensional plane. You may have encountered cross sections before, like slicing through a loaf of bread or an apple. Now we're doing something similar, but with a cone. Because of their symmetry, the shapes we can make have many interesting properties that we can discover. What kinds of shapes do you think you'd uncover from these cross sections? That's what conic sections are all about, exploring the different shapes we get when we slice through cones. Let's get into it. When the plane intersects the cone parallel to its base, meaning when it's perpendicular to the cone's axis, the intersection is a familiar shape. Which shape? A perfect circle. From basic mechanics to modern technology, this shape is all around. For instance, wheels are circles because this shape ensures a smooth ride. The unique property of a circle is that every point on its edge is equidistant from its center. This means that as a wheel turns, the distance from the center to the ground remains constant, providing a stable and consistent motion. Imagine if wheels were any other shape. Your ride would be bumpy and unpredictable. But circles are not just important for wheels. The properties of circles are also fundamental in modern technology, like GPS triangulation. GPS, or the Global Positioning System, relies on the precise measurement of distances from multiple satellites to determine your exact location on Earth. Using the properties of circles, the GPS receiver then triangulates your position with incredible accuracy. This is how you can find your location on a map, get directions, and even track your fitness activities. When the plane intersects the cone at an angle not parallel to the base, we get an ellipse. An ellipse is a closed curve like a circle, but is oval-shaped. It's the shape of many orbits in our universe. The orbits of planets around the Sun are elliptical. Johannes Kepler's first law of planetary motion states that planets travel in elliptical orbits with the Sun positioned off-center. This elliptical path allows planets to maintain a stable orbit and explains the varying distances between the planets and the Sun. Now, if we adjust the plane to be parallel to the slant of the cone, the intersection creates a parabola. Remember that although we've cut these cones down to fit on the screen, they extend infinitely in both directions, which we indicate on the parabola using arrows. Parabolas are everywhere around us, from the path of a thrown ball to the design of satellite dishes. The path of projectiles follows a parabolic trajectory due to the influence of gravity. Understanding this parabolic motion is essential in fields like sports, engineering, and the military for predicting and controlling the paths of moving objects. Satellite dishes use the reflective property of parabolas to collect signals. The parabolic shape ensures that signals hitting the dish are reflected to a single focal point where the receiver is located, allowing for clear and strong reception of signals from satellites in space. When the plane intersects both cones, the result is a hyperbola. Hyperbolas have two distinct curves, often seen in the paths of certain comets and the design of cooling towers. Hyperbolic navigation systems like LORAN, short for long-range navigation, use the time difference of radio signals to determine the position of ships and aircraft. These time differences, when plotted, take the form of hyperbolic curves. and this method offers high accuracy over long distances, aiding in safe and reliable navigation. And as for cooling towers, their hyperbolic shape is not just for aesthetics. It serves several important engineering purposes. It provides structural strength, promotes efficient airflow, reduces material usage, and enhances thermal performance. In this unit, we will take a closer look at each of these conic sections, developing an understanding of their definitions and properties. We will explore their unique equations and how they are represented in the coordinate plane, which allows us to take advantage of these properties and apply them in the real world. And since working with the equations of the conic sections can involve a lot of squaring, factoring, and square root calculation, today's lesson notes will also include a review to refresh your memory on some key skills before diving into each specific type. I'll see you next time where we dive deeper into circles. Hey, hey.